can do a roundtable. You know me, Don. I'm always up for a roundtable, man.
Okay. Hi, everyone. Welcome. We were just talking about Docker and, in the green room here. And I was like, we got to get everyone in so we can get started and not miss out on these spontaneous conversations. So just while it's fresh, Brian Sletten, you were making a point about Docker going away with WebAssembly, if WebAssembly were around. So explain your point there.
Sure. Docker is largely obviously about containerizing behavior and having an environment that you then can have your expectations met about what's going to be installed, and managing those as sort of like overlays. And WASI, the WebAssembly Service Interface, is going to be providing a default set of behavior, kind of like a POSIX layer, but for arbitrary functionality. So it'll start off with files and processes, but it'll eventually include things like cryptography, cryptocurrency stuff, 3D graphics. And so you will write code that will compile to expect to run in a WASI environment that provides those interfaces. And that can be in a browser, out of a browser, in Node, in Dino, in an embedded environment. So the Bytecode Alliance is a big part of moving all this forward, and that includes Red Hat, Intel, Mozilla, Fastly. So I think it's a matter of time before Docker will just cease to be necessary. And Kubernetes has already moved to support kubelets, or crustlets, I think is the name, for their WebAssembly bindings. So anyway, interesting to see.
Very good. All right, so let's get started with the presentation. I'm just going to leave the happy gallery view up here while I go through my boring slides. So you guys can see the slides, right? Or the slide pane? Mm-hmm. Okay.
Yeah.
All right, so I worked a lot on these slides, so everyone please pay attention. Here's a screenshot of our sponsors page from ujug.org. So if you have any choices in life to choose these people or people who are not these people in your choices, choose these people because they support UJUG, including STG. And Brian Hansen, who is a former UJUG board member, is here from STG, the longest running sponsor. I think it's been 20 years now.
Wow. That
we have gotten money from STG, and we have, I wonder how many pizzas that has equated to over the years. Just
a
like,
lot.
Yeah, a lot, hundreds of pizzas, courtesy of STG. So now I will bring up the slide with STG's logo and then turn the time over to Brian Hansen here to talk about what's going on in the market and whatever he wants to talk about.
Yeah, no, thanks, Don. And you guys get the Bryans tonight, so you're doubly lucky. Don and I were chatting about just what to briefly mention to you guys tonight, just kind of local market health and what changes we've kind of noticed here along the Wasatch Front with our industry. Demand is still as high as ever for software developers. There has been, some companies that have had some layoffs and stuff. Fortunately, STG is not one of them. In fact, we grew just under 10% last year, about 8-9% last year as far as our headcount is concerned with consulting. What constituted us having that Docker conversation is asking what technologies we see popping up. And the standard ones that have been there for a long time are still there, as Java, .NET, Angular, React, that type of stuff. But where I saw that conversation kind of going, or what we talked about, was some of the ancillary or kind of satellite technologies are becoming more of requirements. And one thing I noticed last year is a lot of people really buckled down, either for whatever reason. They were unemployed, or they just started taking things more seriously, which is really what I saw. A lot of people just taking things more seriously and really amped up their training. They really just increased their training. So I've seen a lot more people that are learning Docker, that are learning AWS stuff, that are from the Microsoft side of things. They're chasing Azure and doing other things like that are helping round out or beef up their full stack skill set. And I've seen a lot more job recs come through asking for that more well-rounded full stack developer to come through. So it's not just, great, yeah, I know Java. Hey, and I even know Angular or some React or Vue or whatever. It's, oh, well, you've got some AWS experience. We'll choose you over that other guy because you do. So that's seemingly to become more mainstream. So kind of the health of what we got going on. And we just want to say thanks for you guys being around long enough for us to sponsor you that long. So it's getting on 21 years now. But cool.
And
well, thank you, Don.
Yeah, and just so everyone knows, STG secret sauce is you get hired on full time, and then you are an employee of STG, but then you get put on contracts, and then if you're not on a contract, you get put on the bench for training and such. So it's kind of like the cool things with the contractors get to do with with new gigs, and then they can do training. So they have a steady income, but they get to do different things.
Last year, in between projects, we had people complete 109 certifications, and we had 2 people that are amping up to be their full AWS cloud practitioners, and all the myriad of AWS certifications that are out there. They were going through that. I saw a whole pile of different certifications just across the board that they were able to accomplish in between projects last year, which was great. 109 or 110 of them total by the end of the year. Cool. So yeah, we take a huge investment in developing and growing our employees. And you're an employee of STG when you're on. Even though we put you out on different projects, you're still an employee of STG. It's what hired me on there, and why I've been there for as many years as I have. So it's great.
Good stuff. All right, well, let's get on to the rest of the slides. We got upcoming schedule. So this is the first half of 2021. Next month, we've got ultra low latency systems from Goldman Sachs. To be honest, I added the ultra there to make it sound more sexy. They just said low latency, but we're talking nanoseconds here. Can make the difference between being rich and being like Goldman Sachs rich. So learn how to be Goldman Sachs rich. That's the message for next month. And then we've got a security guy, Jake Schroeder, who's amazing. He's going to come talk about the latest threats. You may have heard about a breach or two recently, like, what was it, the entire government, the Russians got into everything.
Parler.
Yeah, oh my God. Yeah, the Parler thing. Oh my God, that was just stupidity though, on Parlers, And then we've got Venkat, and so Venkat is going to come talk about whatever he wants. He's going to talk about paint dry, and it'll be the best talk you'll have heard all year. Besides this one, of course, Brian.
I know where I stand.
No. And then Dave Smith, he gave that Alexa talk. I think it was last year. He's going to come back and talk about continuous delivery. He's a great speaker. If anyone was at that talk, it was just amazing. And then we've got, for the first time in June, we've got NVIDIA coming out. That's going to be a cool talk. We've been working hard to get them for a while. So I'm excited about that. Okay, so door prizes. So everyone is automatically entered for the door prize, but you have to be here at the end of the presentation to get it. I'm going to make you respond in chat to say that you're here and you can use the prize. So we've got 2 JetBrains licenses and the Agile Learner certificate, which is Venkat's. I think it's a month subscription to Venkat's online learning system. It's cool. A lot of great videos, good stuff going up all the time. And that's it. Let's get going. So please welcome Brian. Everyone, I'd like you to chat some welcome or some clapping in the chat window. And then this is Brian's new book. When is it coming out, Brian?
Probably June June of this year. Yeah.
Okay, great. And then for questions, we'll just have people post them in the chat, and then I'll break in and interrupt you. Oh my gosh, look at all those. Thank you for the warm welcome. Can you see all the chat?
Oh, there we go.
Yeah, wow, there's dozens. Thank you everyone for welcoming. I will give him the screen and take it away.
All right, well, thank you very much. It's great to be here. I always love coming to visit there, but I'll take getting a chance to have a chat while we're there. So you can now see the screen, correct? I'm gonna move that window over just so we don't have. Oh no, shoot! That's gonna switch the screen, isn't it? All right. There we go.
I can see. Yeah, I can see your screen.
Okay, you're not getting the mirror of infinity now?
I am getting that off to the side. There you go. That looks good.
Okay. I'll be switching over to some other little windows a little bit later, but for now, this should be fine. I've got the slides are available through this link, tinyurl.com, ujug-ipfs. And I will return to that at the end of the talk, but I'll explain why in a little bit. So this is probably new to most everybody. Maybe you've heard of it, maybe you've looked into it a little bit. When you hear that the name stands for Interplanetary File System, maybe you'll think, okay, well, that's probably not something I need to worry about right now. But I do actually encourage you to pay attention, because the name is in part a reference to J.R. Linklater's original name for the internet, which was the Intergalactic Network. And two, because they are actually imagining this as the basis for an interplanetary file system. The idea is we're sending people to the moon in a couple of years. Hopefully that's still on. We're sending, Elon Musk wants to put people on Mars. And prior to doing so, we're going to need some way of exchanging information with people kind of at an interplanetary level. So I'll come back to what I mean by that. But it's basically a framing device for thinking about the problem. And in essence, if it ends up working well for them, it's going to work fantastically for us here on planet Earth. But it's really a larger, much larger initiative, in essence, to prop up the web into the remainder of the 21st century. It's facing a variety of fragilities. Those fragilities come in the form of, sort of network interruption, the fact that people post stuff and then stop hosting it, and then links break, and we're losing a lot of content. And also because of various censorship kinds of things. So I'm going to be focusing on the technology part of this, but I will end with a discussion of some of the anti-censorship stuff and how it has played out already in the past. So that's the plan. Specifically, the part of my background that's of interest is I've been focusing off and on decentralized technologies for about 21, 22 years. And it all started when I was at a company called Parabon, where we were building an internet distributed computing platform. So think SETI at home, but general purpose preemptive Java-based system. And we were doing machine learning, exhaustive regression systems that use genetic algorithms for feature selection optimizations. We had people who were running thermospheric simulations. We had Monte Carlo-based digital rendering systems. So, this is all pre-cloud, all of these sorts of things. And our system worked well for a class of problem called an embarrassingly parallel problem. And that's, for things that just don't have to chat a lot with other nodes. If you've ever done any distributed systems, usually there's like a message passing side of it. And we were running in Java. So we were sandboxed, and we didn't let the code open up network connections or anything like that. But if the jobs running on all these different computers needed to talk to each other, we weren't going to be a good platform for that at the time. And so I started researching what would that look like. And so I looked into Java spaces and Genie and Juxta and tuple spaces. I've been tracking P2p systems, the various piracy oriented ones. But also things like Bittorrent, which actually didn't start off as a piracy system. It grew out of the hippie jam band community. And what was interesting about it is it built kind of an economic model into the sharing. So no individual had to serve up all of the content, and you would get credit for serving up what you had already downloaded. And that would basically translate to a higher capacity to download from everybody else. And so you couldn't be a leech in the system, but it would work well to sort of like collectively share our bandwidth and get people what they needed to fulfill whatever request that they were looking for. Turns out pirates like that. So that's the name that it has taken for itself. But the technology itself is not intrinsically only for illegal use or anything. And people are now using it to share large data files and to work together and to collaborate. And WebTorrent is a WebRTC-based BitTorrent kinds of system. So You could go to instant.io and open it up, load a file into your browser, and then copy a link and share it with somebody else. And their browser and your browser will federate and find each other and be able to share files without, talking to cloud-based systems and things like that. So I want to talk a little bit about sort of decentralized technology in general and what makes these things happen. But then I'm going to talk about the technology stack with respect to IPFS, how it fits into things like the web, although it's certainly these technologies are usable for other purposes, and basically leave you with a lot of tutorials and resources and things like that to go look at. So I want to start by highlighting a hero. I hope at least some of you know who this is, but if not, his name's Brewster Kahle, and he's behind things like the Internet Archive and the Wayback Machine and whatnot. And so he's got a very strong interest in the long-term health and stability of the web as an information sharing platform. So the fact that links break and that documents that were available in the past are no longer available are obviously a key part of his interest. But a couple of years ago, he and Sir Tim and Vint Cerf and a variety of other folks sponsored a decentralized web conference. And at that conference, he kind of threw down a manifesto and ended with the idea that I believe we can do something quite counterintuitive. We can lock the web open. And so there's a lot of activity in a variety of spaces. You can see some of the videos and some of the talks and things if you go to decentralizedweb.net from that summit. It talks a little bit about the goals and what people are thinking. And you can see another flavor of how this is coming around if you go to web3.foundation. This talks about things like the Polkadot project and grants that are being given to groups and organizations to help facilitate decentralized systems. Because at the end of the day, it's much harder to build decentralized systems that handle scale and flexibility and work well. So I'm not here to say decentralizing is wholly good and centralization is wholly bad. The value proposition of some of the centralized social networking sites and things like that is they're able to index the content. They're able to optimize the experience. Part of the reason why sites like Facebook are so popular is because there's a very low inertia for sharing stuff. Sadly, maybe not enough inertia given what gets shared. But the point is, there are aspects of centralization that are positive, but there's also often some fragility. If you don't have the bandwidth, if you don't have the infrastructure, if you don't have the server capacity, then it's kind of hard to meet the demands of a large-scale social network. And so we've seen attempts at decentralization in the past. So the Diaspora project was a spin-off after everyone got mad at Facebook a couple of years ago. I don't remember which thing it was about Facebook they got mad at these point. But they did like a GoFundMe and got a lot of investment and went off and created something that very few people use. It's well engineered as far as I know. But that highlights one of the main problems with decentralized systems is it's not just a technology thing. It's also a community thing, and it's also a developer thing, and you need to have all of those things come together in order to be useful. Another one you may have heard of, and maybe even some of you use, is called Mastodon as sort of a decentralized Twitter. And that actually gets quite a lot of activity. And what's kind of cool there is you could run your own Mastodon server. You could attach an account to an existing shared community server, but the whole thing is decentralized and talks to each other. Kind of like in the old Usenet days, if there are any oldies like me hanging out there as well. But there's some fundamental technologies that have been successful, and I want to highlight those first before I start talking about IPFS in general. So one of our first real mass scale decentralized kinds of systems was actually a hybrid model. Obviously, most of you will have heard of Napster, but the youngins may not have heard about this. This was sort of like where pirates went before BitTorrent to share music. And it used something called a distributed hash table. And the idea here is the content itself would be run through a hashing function, which is a one-way transformation, but it generates a fixed size output based on the algorithm at play of arbitrary inputs. So it doesn't really matter whether you're talking about like a one-page text document or a 5-minute song. It will end up hashing to the same kind of key, and that key is useful to identify the content. So the idea was all the peers that were on the network would publish to Napster what files they wanted to share, and then Napster would basically index it. So if somebody came along and said, you know, hey, I want the new Bieber song or whatever, I don't think Bieber was alive back then, but whatever, you know, you say what you want, and then there would be these keys coordinated with metadata to indicate, you know, these people have that song, and so they were able to share the files that way. Now, unfortunately for them, the index and the name and the branding and the notoriety were all centralized around the Napster name and brand. So it made it very easy for the MPAA and the RIAA to come and sue them, basically out of existence. But technologically, it was a phenomenal system, right? It was one of the first real mass scale sharing of large amounts of data that we had seen. So the distributed hash table is a very important concept. It shows up in things like Kademlia and some of the other decentralized systems that are out there. But the main issue is there's no real sort of index to the keys, and therefore trying to maintain that index in a centralized way is a time-consuming kind of thing. Now, in response to that, sites like Gnutella said, okay, don't tell us anything. We will just run queries against all the nodes, and whoever has the stuff that somebody's looking for, respond, and we will route you towards those nodes. Unfortunately, that kind of sucked technologically because you never knew whether a node was going to respond or not. There was a lot of gossip chatter about the comings and goings of nodes, and that's just it's a big waste of bandwidth, right? So that just didn't work as well as Napster did. So if you want to invest some time into understanding some of these core technologies, I encourage you to dig into distributed hash tables and see how they end up showing up in a wide variety of decentralized systems. It's kind of a necessary but insufficient starting point for thinking about being able to locate arbitrary content in a widespread way. In the early 2000s, there was some work that was done, a joint research project between Rice University in Houston, Texas, and Microsoft Research called Pastry, and eventually became known as Free Pastry. But this was an attempt to build what's called a network overlay on the back of a distributed hash table kind of system. And the take-home message is that this was a network that would grow logarithmically. So, for example, if you had 1 billion nodes on the network, it would take no more than 9 hops to route a message from any node to any other node. And there were both sort of like geographic proximity measures as well as logical proximity measures. And so there would be like these neighborhoods of logically connected nodes. And this was a way of assigning responsibility for certain pieces of content. So in this diagram here, the node 65A1FC at about the 7 o'clock position there may say, I want content, and be told that that content is the responsible node for that is the D467C4 at roughly the 2 o'clock position. And so if I wanted to issue a request to ask for that piece of content, I would only have to know enough to send a message to something that was logically closer to it. I didn't have to have the actual routing table. And this is why there were so few hops. This is why there was no sort of gossiping of the comings and goings. ultimately only 6462BA would really have to know whether C4 was there or not. So it was just a lot better of a use of bandwidth, routing mechanisms. So network overlays on top of things like distributed hash tables were a big part of moving things forward. One of the other big steps forward was the adoption of what's called content addressable storage. Now, many of you I know have heard me talk about REST and semantic web and things like that. And I always said, let's use standard identifiers and, where possible, standard, stable, resolvable identifiers. Those are very useful. And if you go to the trouble of curating your URIs, that can be a very, very powerful property to bake into a naming system. Is not only is it global in scope, but it's also resolvable. The downside is it's also very fragile, because if you just decide, I no longer want to serve this thing up, or if you have named it badly, like we tend to do, CGI bin.pl.php.do. Who cares, right? If you change your technology, then obviously you sort of no longer maintain this old system anymore, and that stuff starts to disappear. So the idea behind content addressable storage is that we will know our files by their identity, and their identity comes from a hashing function like in a distributed hashing table. This is also why we can know that if I ask Don's node for something and he returns something to me, he's not going to rickroll me, because if what he sends me doesn't hash to the content identifier that I'm looking for, I'll just reject it, right? That's not what I'm looking for. But now what we've been able to do is we're able to give identity to our stuff, and it doesn't really matter who gives it to you. If 12 other nodes have copies of the thing that you're looking for, we have some security and confidence built in that the thing that you're looking for is going to be provided by one of them, and you're not going to accidentally get some malware or something else. Now, this is not an unusual concept, and probably almost every one of you have used content-based addressing if you use Git, right? Git was a step forward in a decentralized kind of system, a CM system, compared to Subversion and what came before, in part because it did use content-based addressing. So if you check in a file, it's given a hashed sum, and that sum is its identifier. So if you check the same file in multiple times, there will only ever be one copy. So the object database in Git identifies the content based on their identifiers, and branches and things like that are really just playing around with metadata. And so the latest version will always point to whatever the latest version is, but a branch or something like that doesn't actually need to copy the files around. It just copies metadata around. And so this combination of distributed hash tables, network overlays, content-based addressing provide a lot of the details that are going to make a system like this successful. But the next part of it is needing to know when things have changed. And so that's where data structures like Merkle trees come in. And if you've ever looked into the implementation of like Cassandra and things like that, a lot of those systems will use Merkle trees as well, named after the venerable Ralph Merkle, who kind of got shortchanged in the Diffie-Hellman key exchange naming. Diffie and Hellman always wanted to call it the Diffie-Hellman-Merkle key exchange because they based their work on his work, but it didn't stick. So it's good that he gets his name on some other stuff. The idea behind a Merkle tree is that there is one hash that sums up all of the pieces of some content. So if we're talking about an image or a song or a movie or something like that, obviously there are going to be lots of blocks, and each block is given its own identity. So at the bottom of this tree, we see L1, L2, L3, and L4, and those will have their individual hashes applied to them. But then you can hash the hashes. So hash 00 and hash 01 becomes hash 0, hash 10, hash 11 get hashed and become hash 1. and then you hash 0 and 1, and that becomes the top hash for the entire tree. But this now gives us a very efficient way of detecting when something very specific has changed. So if whoever is responsible for this file updates the image and adds, a couple of pixels that affect just block 3, then block 3 will no longer hash to the same value. Therefore, the hash of 3 and 4 will no longer hash to the same value, and then the top hash will no longer hash to the same value. But I can follow the tree and basically determine what has changed, and then with respect to asking for these things in a decentralized way, I only ever have to ask for the pieces that have changed. So if I have an efficient routing mechanism with the network overlays, if I use content-based addressing to identify the individual pieces, we're really sort of solving a lot of the overhead problems that we would see in a decentralized system. So there's obviously more to it than that, but that's the kind of thinking that goes into the design of a system like that. So IPFS is an initiative. It's been around for several years. I've been talking about it for a while. It's largely sponsored by a company called Protocol Labs, and they call it a peer-to-peer hypermedia protocol designed to make the web faster, safer, and more open. And what's cool is they have broken it up into a technology stack, and then they peeled each technology stack off. So they want people to use the individual layers without necessarily having to commit to the entire thing. And so one way of thinking about the IPFS stack is as if you merge the web, self-certifying file systems, decentralized change management systems, economic decentralized sharing protocols like BitSwap and Bittorrent, and then the capacity to name and identify and request arbitrary pieces of complex Merkle trees using distributed hash tables, right? So it's really all of these things together gives you a sense of what's going to be possible here. Now, the specs are very, very well designed. They spend a lot of time on this. But I don't want to start there. I want to leave that as a placeholder, and you can go read through these things if you want. But I want to highlight basically the tiers, and it looks a little bit like the internet architecture stack. It looks a little bit like the OSI reference model stack. But the three main layers are the layers that are responsible for moving the data around, and that is largely handled by a technology called Lib P2p. And then there's a linked data model, very much influenced by the ideas behind RDF and semantic web kinds of things and linked data technologies. But we're linking arbitrary blocks. And we have a common data structure that allows you to link arbitrary blocks. And so that's manifest in a technology called IPLD for interplanetary linked data. There's a naming system that I will highlight a little bit later that's available. And then the applications will be built to use the data. And so the web is just one type of application that was there. So when we think about Git, does anybody happen to know what Git uses for a hashing algorithm? And if somebody says, Dan, or Don, can you just read it out, please?
I don't see anything yet.
Okay.
I hear people Googling. I hear people typing though. So.
The answer is SHA-1. And if you have followed the history of SHA-1 over the course of its lifetime, you know that it was originally designed by the NSA. And it was a well-trusted hashing algorithm for quite some time. Something like MD5 had been broken cryptographically many years ago. About, I forget, time's an artificial construct. About 15 years ago, I guess, I remember starting to hear rumors that SHA-1 collisions were starting to become possible, but very expensively. Like you needed to throw nation-state level resources edit. But these days, SHA-1 is considered broken, right? And you just need a fair amount of resources, but not an unheard of amount of resources. And so it's possible to generate collisions. And that's a problem, specifically for things like certificates, because if the same inputs can generate the same hash, then we can no longer use this as the basis for identity. So the problem with Git using SHA-1 is that all of the objects are SHA-1'd, right? And now SHA-1 is broken because there are hashing results out there that can't be trusted anymore from a purely identity perspective. And it's not as critical in Git as it is in, say, cryptography or transitive trust in the certificate models, right? But if you think about how many programs out there assume that a Git hash is a SHA-1 hash, how many scripts out there assume that the hash value is exactly 160 bits as a consequence, and how many tools will break when these things change. And these things are changing because if you go check out shatter.io, you can read about how SHA is broken and it's no longer suitable for identity purposes. So therefore, the Git community is now translating, moving away from SHA-1 towards a stronger hashing function, something probably along the lines of SHA-256. That version of SHA was also designed by the NSA. And once SHA-1 started to become, people were concerned about it from a collision perspective, they began to get a little concerned that SHA-2 might have the same problems, right? Because they're based on similar underlying structures. So SHA-3 was actually a competition around the world, and things like Blake and Kikak and a bunch of other hashing algorithms were proposed. Eventually, Kikak was chosen to be the basis of SHA-3. But the idea was like, let's just pick a different underlying structure that performs well and isn't known to be even remotely compromised, so that you're encouraged to use SHA-3, SHA-384, or whatever, for cryptographic purposes. But for the time being, SHA-2 should be fine for Git because there's no known hashing collisions. But the question I want you to stop and think about for a moment is, what does that do to the longevity of all the references of all the GitHub repos? Right? We now have to have some kind of en masse translation function to go through and rehash everything, re-identify everything. And that assumes that SHA-2 isn't going to be broken anytime soon. At some point, SHA-2 will be broken again. And so then we're going to have to go through this all again. It's exactly that problem that led to the development of a series of technologies in the IPFS stack called multi-formats. And so the idea is, rather than just having a simple hash function and therefore this opaque key, the idea is these kinds of references will be self-describing. So multi-formats is really a collection of technologies like multi-hash, multi-address, multi-base, that are designed to be resilient, self-describing approaches to things like content identification with an eye towards the future. So we're trying to make the web more stable. We're trying to make it secure. We're trying to give it some longevity so things don't break all the time. And so it's worth it to design that into the system. So, for example, a multi-hash, rather than just being the digest itself, which was the case with how Git used SHA-1 and how most people use hashes, instead it will be a 3-part type length value pattern record that indicates the hashing function, the digest length, and the digest value. So this is an unsigned varint. If you're not familiar with varints, this is an extensible integer representation that for small values uses a small number of bits, but uses an increasingly large number of values for a larger number of bits. Also useful in this kind of a situation because you don't have to, say, commit to a 64-bit representation of a number, say, and yet we still have a path towards extensibility. So we can start and have small numbers to indicate the numbers like 0, 10, 20, 100, 150. But once we start getting up into thousands or 10,000s or 100,000s, we've got room, and the varants will expand to be able to address those things. But when we're talking about things at web scale, being able to save a couple of dozen bytes here and there for something that's going to be impacted by every request for every piece of content, that's a lot of bandwidth to save. So again, it's this kind of thinking that is really providing the stability and the long-term vision for this technology stack. So for example, if you're going to use the SHA-2 256 algorithm, there's an existing table that identifies that as a code of 12. That is a 32 byte hashing algorithm. Sorry, 32 byte. Yes. And so that's represented in the hex code 20, and then the digest is the actual one. So we can see that 12, 20, and then the digest is the unique identifier based on this multi-hash. So the idea is, like, if you come across a reference to a content identifier and it is self-describing, then you will know how to parse it. And at that point, you can then go and update it to a newer hashing algorithm if you want to. But that doesn't have to be like this whole scale en masse rehashing of everything every time we roll to a new hashing algorithm. So you can see that, again, this is a technology that has its own spec. There are implementations in all these different languages. So you can end up building this into your own software. So if you do use content identification, or if you want to move in that direction, this is an important consideration. It's like just hashing it once is probably a bad idea. Committing to a self-describing, evolvable identification scheme is a much more stable approach to that. So in addition, there's also ways of describing things like different network addresses. So if I gave you this address, every single one of you would be like, cool, yeah, no problem. That's an IP4 collection of 4 octets with a port number. And then if I gave you this, most of you would say, okay, yeah, that's a IPv6, and with all the trailing zeros left out, or the preceding zeros left out. But once you start getting into like arbitrary references to arbitrary protocols and arbitrary network stacks, and whether you're using DNS or these sorts of things, you're assuming that the code or the application, whatever is catching the reference, is going to know what to do. So just like we have self-describing ways of referring to hashes, we also have self-describing ways of referring to network protocols and addresses and things like that. So this is a way of saying, I want you to use IPv4 to communicate with this node point using UDP on this point and the QUIC protocol. If you're not familiar with QUIC, QUIC is a thin layer on top of UDP, and it also forms the basis of what's going to be different between HTTP2 and HTTP3. So HTTP3 is going to not be based on TCP anymore, which may surprise you, but there's some fundamental underlying limitations to how TCP expects to deal with network congestion, and how HTTP basically wants to be able to like fetch as much as possible up front and then kind of go quiet. And so there's just a mismatch between how does TCP work at the transport connection layer, and how does the application of HTTP3 want to use it. So you'll start to see more about QUIC if you haven't already. But notice these are now self-describing network references. I want you to do a DNS lookup using DNS over IPv4 and look up via TCP IP and da-da-da-da-da. So you get the idea. We've got self-describing hashes, addresses, encoding schemes for whether this is like a base 64 encoded thing or a base 58 encoded thing. If you've done anything with Bitcoin, you know that Bitcoin addresses are basically base 58 encoded to avoid confusion. because there is no chargeback or anything with Bitcoin. Once you send your money away, it ain't coming back, and that's a problem. So to avoid confusion, base 58 eliminates like capital O's and ones and lowercase l's because those could be misinterpreted. So it's like base 64 but 6 less because those 6 characters are potentially confusing. So this is a very low-level set of functionality, but it provides this long-term, future-proof way of dealing with content addressable stuff. And just to show you the same content here from the website, if I take the name Merkle Damgard, which is the underlying hashing engine in essence, and I take that string and I hash it with SHA-2, SHA-1, it'll be 160 bits. SHA-2, it'll be 256 bits. SHA-2 with 512 will be 512 bits. The Blake hashing algorithm will hash it to 512 bits, etc. So, you know, the same content can be known by different hashing algorithms, but when they are self-describing, which these ones here are, then it's easier to go ahead and future-proof the references. So these are all just other links to that whole multi-formats thing. Any questions or anything before I move on? Hopefully it's clear why that's interesting and useful.
Not see any questions.
All right. So that's really just low-level identity kinds of things. How do we make reference to stuff? The next part of this is how do I actually network? And so Lib P2p is the next part of the technology stack. And this is an independent open source project. It is really, really well designed. You can build modular network applications on top of them. It allows you to use multiple transports. Your same application can be communicating over WebRTC and QUIC and HTTP 1.1 over TCP. You can start with one protocol and move to another. You can do protocol muxing. So if you detect the most efficient protocol for you to use is this one, then you can like multiplex other requests over that. It's got support for obviously encryption and upgrading and working inside and outside the browsers, dealing with high latency scenarios like if you're off in the wilderness, right, or camping or something. So this is a lot of really nice technology at play here, and it provides the basis for the multi-protocol efficient use of bandwidth that IPFS ultimately uses, but it is independently available for anyone else who wants to use it. So there's some really great documentation. They're very interested in helping people understand these things. So here we have a series of concepts about identifying peers and establishing circuit relays and secure communication mechanisms and generating pub-sub kinds of communication protocols, multiplexing multiple streams over another one. So lots of good conceptual documentation, and then obviously the specs and a series of tutorials. So for example, with the JavaScript implementation of this, it walks you through establishing the connection, configuring Lib P2p, establishing an initial node endpoint, hooking in other dependencies. So it's all very modular. So if you don't need to use encryption, you don't really pay the penalty for it. So notice this one pulls in Lib P2p itself, TCP as one of the protocols it uses, the ability to use the noise protocol for encryption. So again, these tutorials will walk you through using an increasingly large amount of the functionality, listening on an individual ports. You'll notice that is a multi-address reference, right? So this is just a concrete, self-describing, declarative way of saying, I'm listening on IPv4 at this endpoint using the default or a random port and TCP. So there's no confusion, and there's no special knowledge that you have to be able to resolve certain kinds of network references like that. So again, the tutorials will walk you through setting up. If you want to play with the Go ones, they're there as well. Eventually, you can start pinging a node, and it will respond with a pong message, and you can see how you can establish these communication patterns. All right, so there's also a ton of videos and talks and things that go through and highlight some of the design decisions and some of the newer features and whatnot. So I encourage you to go check out some of these videos as well. This is a very active community, and these things are changing quite a lot. So you can see, even back to some of the Decentralized Web Summit conferences in the past, how these ideas emerged out of it, and now IPFS is sort of one of the leading players in the space. There are others. The DAT protocol evolved out of the open science, open access community. There are other things like I2P that are in this space. So frequently you'll see different conferences where all these players come together and kind of talk and learn from each other. But IPFS is its own technology stack, its own organization, and a lot of people are building on top of those various protocols. All right. Now, with these kinds of systems, layered architectures, you often want to have a compatibility layer, right? So in this case, we have the applications at the top, we have the transport protocols in the second layer. They all are based on an IP portability layer. But underneath that, there's various hardware communication protocols and low-level data link, physical kind of connectivity sorts of things. But if the upper protocols don't have to care too much about the lower protocols, then it's generally easy to switch between them. We've seen that, right? We switched from Ethernet to Wi-Fi, and all of our stuff up here mostly didn't care. But that's what Lib P2p is doing, is giving you the ability to sort of like swap out underlying communication mechanisms for routing things over satellite, radio, carrier pigeons, whatever. Now, on the back of that is also the idea that I want to be able to make references into all of these different endpoints and have those references work over these various protocols as well. So all the applications at the top are things like, collaborative communication or text editing apps, video sharing, content management systems, decentralized ledgers, those sorts of things. I want to be able to point into any of those applications and have those references be valid over any of the discovery and routing mechanisms as well. So that's where IPLD comes in. This is probably going to be the least clear to you exactly what it is and how it works. But again, they're trying to improve the documentation and the tutorials and everything. But if you know anything about linked data and RDF, it's very similar. You have links that point to content. That content is identified through some kind of identifier. It's just we're not using URIs per se, we're using content identifiers. And content identifiers are basically multi-hashes that are generally encoded in some way. The data model is a graph model, but it's a graph model built around the concept of Merkle trees. So it is called a Merkle DAG, a Merkle directed acyclic graph. So this is how the top identifier for a piece of content can, say, point to its blocks, but if that content is in a directory, then the directory could have its own SID, and the files in the directory could also have links. So from the directory, I can find a link to the files that are in the directory, etc. But as you'll see momentarily, you can also link into Bitcoin transactions or Git commits or whatever you want, right? So it's a very, very flexible mechanism, but basically it's just about linked data structures that are identified using content-based addressing. So I'll let you dig into the details a little bit more. It'll be clear in just a moment exactly what that looks like. So we have an image, right? In this case, an image of a cat, and the cat can be converted into its raw binary format. I could generate a digest of that in some kind of hashed function, but the SID, the content identifier, is going to be a multi-hash. It's going to be a base 64, base 58, but some encoding mechanism of the multi-hash. So it is a self-describing encoding of arbitrary hash function that identifies arbitrary content. That is a lot. That is a mouthful, but basically it ends up becoming this unique identifier. And all the Q's and stuff that you're going to see, or the lowercase b's, is really a function of the encoding and the hashing functions that are there. So now an image could be really a collection of blocks. So the image itself has a upper level Merkle hash, and its hashed blocks will have their own hashes, and then sub blocks can have their hashes, right? In theory, that's how this could work. But the base SID really becomes a tree that refers to the hashes of the blocks, and those blocks can then be fetched independently. So the DAG, the directed acyclic graph, is the graph that starts at a single identifier and then continues on into other parts of the world, just like the web does with URLs.
Brian, we had a question. Someone asked, when you say Bitcoin, do you mean blockchain?
I mean the Bitcoin blockchain, the Bitcoin decentralized ledger.
Okay.
All right. So the goal is eventually, hold that thought, the goal is eventually to have browsers and libraries and tools like that just natively be able to communicate with IPFS. But this has been a long time in coming, and there have been a variety of bootstrap processes. So as an example of bootstrapping the process, if you wanted to play around, you could go install the IPFS command line tools. And those were originally written in Go. There are now increasingly other languages. So JavaScript is a first-class citizen in this space. Rust is increasingly becoming one. They're very interested in having good Rust support. Java lags a little bit in some of the implementations, but I think there's momentum to fix that. But the idea is you could initialize a node, and just like a blockchain node or a Bitcoin node is known through its public key identifier, an IPFS node is just a key value pair. So the node has identity, the node has a hash, aka a multi-hash, but that becomes a unique stable identifier for the node. And so once you install the tools and once you initialize the node and give it identity, then you could use the tools to ask for things that exist on the IPFS, decentralized system. So we initialize it, and at the end it says, oh, hey, you can say IPFS cat, and then give it an identity. So this refers to some node or some directory, right? And then in that directory, there is a file called README. Now, this is just an optimization, right? The README file has its own identity, and if you know it, you could just ask for it. But what this allows me to do is to ask for the file README in that directory without having to go ask that directory for its contents first, get that back, look for the file README, and then ask for it. So it's kind of like a fragment identifier, right? I want that piece of the thing that I'm asking for, but it's just an optimization. So I don't have to go and have round trip requests that are just going to be annoying and useless in the long run. So what you can see here is IPFS doesn't really need to ship with its own documentation, because you can just ask for the documentation from the IPFS decentralized system itself. So that will end up printing out something like this, because it goes out and it talks to other nodes and says, hey, can I please have this file? Now, chances are a README file is going to be a single block, so it's just going to ask for the one block. Who's got the block? Obviously, the README file for the platform itself is going to be pretty widely available, so anybody can return the block and give it to us. So it comes back, and it's just a text file, and so it says, hey, here's some other things that you can do. Like you can learn about the project. You can do a quick start. So if you turn around and say IPFS cat the same node / quick start, then we're going to ask for the quick start file from the same directory. And it's going to say, hey, you can echo a string into a file and then say IPFS add the file. That will add the file to your local node and give it identity. At this point, it's not sharing anything yet. But it's a way, this is the mechanism for adding things to IPFS. Then you could say IPFS cat, and this will give you a hash value. You could ask for the hash value, and it'll show it to you. It's going to be pulling it from the local node, though. It's not going out and fetching it from anywhere else because nobody else knows about it yet. If you want to add a directory, you can create a directory structure. This is showing that the content addressing only ever has one copy. So if the same content shows up in 2 different directories, it will still only be in there once, but the directory will have a link to the content, so as will the other one. So the tree is still there, the Merkle DAG is still there, but there's only ever one copy, right, of the file in this case. So then you can recursively add the directory by saying IPFS add -r in the foo directory, and all of that whole structure will now be available to your local node as well. Now, the command line tools aren't obviously pulling stuff from your node because these are things that are available someplace else. So they know how to go out and do discovery. There are like bootstrap starting locations, DNS lookups. The IPFS tools can use MDNS, multicast DNS, zeroconf local network discovery. So if you've got a couple of IPFS nodes running on the same local network, they can find each other because that's the most efficient way of resolving content, right? So even though your content is not necessarily being shared yet, the tool itself is able to go out and fetch things. So in this case, there's a cat JPEG, and I can IPFS cat the cat JPEG, and that will store it in a file. Obviously, I can't use the actual cat command because the actual cat command only works on files, right? And doesn't know anything about IPFS. But IPFS cat is aware of the way of looking up and finding these things. And so that will then pull the entire image and all of its blocks into a local file and write them out in the right order, and you now have a copy of this file locally. It is efficient enough that on good networks for well available content, you can stream video out of IPFS. So if you use a streaming video player like VLC, you can pull content out in effectively real time. Once the buffering and everything gets handled. All right, so let's say that I want to add a file called I want to echo iHeart IPFS and then echo my username. That would be Brian. I could then pipe that into IPFS add. That would give it identity locally, and I could then IPFS cat the result, and it would say that's what's there. Now, obviously, this is still just local, but if some other Brian who spells his name properly, so not Brian Hansen, because he uses a Y instead of an I think, right? And sorry, that's a little Brian joke there. There would still only be one copy of this file around, right? For all the Brians who spell their name the way that I do, there would be one copy with one identity. For all the Brians that spell their name Brian with a Y, there would be one copy. But again, this is where the content-based identity is useful, right? This is the thing that I want. This is its identity. Therefore, who's got a copy? Who can give it to me? All right, so let's say that I have a directory, and I go into that directory, and I see that there's a series of JPEGs and a GIF and a movie and a couple other JPEGs. I can then say IPFS add -r current directory. So it's going to go through and say, okay, that image is known as this. This image is known as that. So each of the files has their own identity, but notice the directory has its own identity as well. So this was that convenience that you saw me using. I could ask for the details about the file image3029.jpg in the pics directory, or I could just simply ask. So that would be relative to this node, right? Or I could just ask for it itself because it has its own identity. So if I do an IPFS ls on the directory node, then what I get back is the list of the files, and each file has its own identity. If I say IPFS ls on one of those files, what I get back are the identity of the blocks in the file. And that's true of whether I say IPFS ls relative to the directory, the file name, or use its identifier itself. So see here we have SVHJ63R. If I go back and look at the image 5.4, we have SVHJ63R. So the first time I'm asking for it relative from the directory that it's in. The second time I'm asking it for that specific file name. But in both cases, I get the same collection of blocks that represent the contents of that file. So you see the Merkle DAG going from, the node to the directory in the node to the files in the node to the blocks in the file, and that's all captured and navigable in the IPLD structures that you request from the network. So if you go back to the IPLD.io website, when the slides that I pointed you to a little bit earlier, then you'll see the structures there. All right, so at this point, I want to publish my content. So I will start up the IPFS daemon. That will do a couple of things. That will start up and reach out to the Bootstrap DNS locations. It'll say, hello, I'm a new node, and here's what I have. And can you please tell me about who else you know about? So the IPFS daemon comes up, starts asking questions, talks to all these other running nodes all over the place. But notice it also starts listening on various ports. And notice we're still using the multi-address, so it's telling you exactly how to talk to it on any of those ports. But it then opens up an HTTP gateway and opens up an API server on port 5001, which we will talk about momentarily. But at this point, once your daemon comes up and once it's talking to everybody else, within a matter of moments, if you ask it for its peers, it'll be like, oh yeah, I found 300 of these guys. And notice, the peers may be listening on different ports. It may use different protocols, but all the other nodes are sharing and talking about how rich the network is. And so I can find these through the Bootstrap ones. Once I find other peers, they can tell me about other peers. I can look on local link network activity, and it'll detect these as well. So this is how you start to learn about who to talk to find stuff efficiently. But this is also how you start to announce to the world what you have to share as well. So at this point, the files that I've added to my local node will be visible. So they run an HTTP gateway. So far, in order to deal with any of this, I had to use the command line tools. But now they're listening out there on port 80, right? And so anyone in the world can turn around and ask for an image or a file that I have posted. So here's my iHeart IPFS that's available, or this one, which is that directory that I listed. I can turn around and ask for individual files from that directory. So this is my dog. And notice I'm going out from my network over DNS to IPFS.io to them. They're asking for the content, so it's being routed to them. then it's coming back to me as the HTTP response, and I'm getting the response. So here's the GIF. Notice I haven't asked for that yet today, maybe, so there's a little bit of a lag. Because again, I'm issuing an HTTP request to the gateway, and the gateway, in essence, is reaching back to talk to my server and pull the pieces out. I'm not gonna let it go. It'll eventually sort itself out. Normally, obviously, this is not how you would go about doing that, right? It's a long way of getting there. But I'm just showing you that we have various ways of asking for things. Now you'll notice, that's not IPFS.io anymore. That's Cloudflare. And so this was one of the first really exciting things that happened, was when Cloudflare started fronting IPFS and also terminating HTTPS connections. So that's important because it's very unlikely that anybody is going to block Cloudflare. They may decide to block IPFS.io. In fact, the first time I ever talked about this stuff in a big way professionally was at the O'Reilly Software Architecture Conference in New York several years ago. And on the plane on the way there, I was going over my slides and trying to make sure that the examples and everything worked. And I realized, it seemed like United was blocking access to IPFS.io. And I thought, oh, shoot, I guess I'll have to wait till I land and get to the hotel to check that. Then I thought, wait a minute, they're probably not blocking Cloudflare. And so I was able to go and fetch my content over Cloudflare, even though they were blocking the normal way of getting there. And so this is why the content-based identity, right, doesn't matter where you start asking for it. As long as somebody has the content, they can share it. So this is now fronted by Cloudflare, TLS terminated, meaning nobody knows what I'm actually asking for. It's unlikely to be blocked because Cloudflare is so important, but it also is geographically distributed using Cloudflare's infrastructure. So that's an important way of making interacting with IPFS be so accessible to the typical user. Is you don't have to know anything. You can just ask HTTP or HTTPS servers to give you the content. And let's say this is content somebody doesn't want out there. Well, they may try to block this. Okay, well, somebody else could put it up. Okay, then they'll block them. 3 other people could put it up. And you start to get a sense of how the anti-censorship stuff is potentially factoring in here as well. I will come back to that in a little bit. All right, so as far as the local services, it would really be kind of dumb for me to go out to IPFS.io to come back to my machine to ask for things. So my local node has this stuff available as well. And obviously, it's instantaneous, right? If I ask for this, right? So this is now running locally. And if I ask for that GIF, obviously it's going to be instantaneous because it's being served locally, right? So my browser is pulling it from my own machine over a local link network, but it's the same file, right? So here's a video of my dogs mooning because they can't be with me wherever I was for whatever reason. So the point is, having alternate routes to get to things is both strengthens things, right? We're not tied to a single location-based identifier. Because this is a self-describing hash into a file that's available that anybody can serve up, if one person decides, I don't want to serve this up anymore, somebody else can serve it up. And so again, you can see how this starts to align with some of the goals of like the Internet Archive, is that we have content that's out there, and if for whatever reason you decide you don't want to share it anymore, somebody else can pick up the ball and do so. Now, this is me pulling content from IPFS, but because I've already done it, it's cached and instantaneous, right? So that's the cat being pulled out of the network as well. So My local network is able to serve up content out of IPFS over HTTP, but it also has a local web UI, and that gives you insight into what's going on. So here's, I'm currently hosting 154 megabytes. I've got 303 peers. My peer is this. I'm using the Go IPFS version 7, so that's a very recent version. I can check the status. I can look at the files that are available. I can explore other trees. So the NASA Apollo project archives are available. So I just clicked on that link and notice I got back a JSON representation of an IPLD structure. In that structure, there is a directory called albums, and in albums, there are a variety of files. And again, notice I'm just navigating the Merkle DAG, but now I'm looking at an actual image. And if I want to see it via an IPFS gateway, then it'll actually be served up with the metadata so the browser knows how to identify it. So you can see that we have these really high resolution images from the moon. That's pretty cool. Let's go back to the Explorer. You can link into a specific Ethereum block, right? And now you can see, which block is this and what are the contents of the block. And so now imagine a scenario where you are paying somebody for something, and you issue a transaction, and the transaction goes through, and you want to provide evidence of that. You can now link to it and say, here's the evidence that I paid you, and now give me access to whatever thing I'm asking for. So we can mix and match, files, link into GitHub repos, particular commits. Here's XKCD, cartoons available, right, as stuff being pulled out of IPFS. So very, very, very neat. Now, I'm going to hurt your head. I'm just warning you beforehand that I'm about to hurt your head. If you look closely at the URL there, what do you notice? The application that's being served up through the local port on my browser is just an application that exists in a directory. So there's a directory out there that if I say IPFS ls on it, gives me all the contents of the application, which includes the index.html. So if I say cat index.html in that directory, it will say, oh, you need to pull in these other things. And these are going to come in over the same HTTP channels as the other ones. So I can now serve up a web application through a local HTTP proxy, pulling content arbitrarily from anywhere out there in the multiverse. Think about that for a second, because it's even weirder and more cool and more powerful than you're imagining. Because this is content identity based, meaning a particular release of an application has a particular identifier. And if you go and add a new version of your web application, and let's say you only touch the JavaScript and a style sheet and add an image, how much of the rest of the application has been modified? None of it. Therefore, all of its content identifiers are still the same. Now, we're changing some things. So now there will be a new top-level view of the directory from that content version. But guess what? The old one is still there too. And so what this shows you is, unlike now, where if you deploy a new version of your application, everyone has to use the new version of the application. But not only will this update only involve, in essence, uploading the things that are different, everyone who wants to use the old version can still use the old version. And by the way, who's hosting it? The answer is nobody. You want to talk about serverless architectures? This application is being served up through a local HTTP server on the machine that you're browsing it on. I do not need to post this and host it in the cloud. I do not need to host this someplace else. And by the way, if I'm also sending you things like WebAssembly modules, those can be written in any language, C, C++, Rust, Go, Python, right, whatever. And they are completely portable. The same WebAssembly code will run on Linux, Windows, Mac OS, whatever. And I hope you're starting to get a sense of the fact that your world is changing very, very fast and very, very cool in very, very cool ways. So this is now a Cloudflare fronted SVG. For those of you who've seen me talk about WebAssembly before, know what's coming. This is the SVG being pulled out of IPFS. It has embedded JavaScript that has a timer that is calling into a physics engine written in C++, compiled to WebAssembly, also pulled out of IPFS, and it is positioning the sand elements from the physics engine, and those sand elements are DOM elements, part of the SVG document. So an SVG document pulled from a decentralized system, served up to my local browser in a geographically distributed content delivery network friendly way over TLS. This will run on Windows, this will run on Linux, this will run on Mac OS. There's no difference. It will run everywhere.
We had a question, is there any way to purge content?
Yes. Stop serving it up. Right? Because keep in mind, where is this content coming from? This content is coming from local stuff, right? I'm serving things up locally. It's able to find these things, right? So if you don't want to serve something up anymore, you just don't serve it up anymore. Now, if somebody else has a copy of the blocks, I can't stop them from serving it up, right? That's kind of the whole point. But if you just decide you don't want to serve it up anymore and nobody else is asking for it, eventually it will be sort of flushed out of the system, right? If I don't give this talk for a while and I come back and I try to like start up IPFS right before the talk and then try to click this link, it's not going to work very well because it's got to, find the blocks and ask for them. And eventually, as you see, it's instantaneous, but there's a little bit of network hysteresis, right, that has to be resolved in terms of the blocks showing up in the right place.
Now, we had a couple more questions.
Okay.
First one is, can you speak to the announcement that Brave now supports IPFS?
Why you gotta ruin my thunder? Yes, I will talk about that later.
Okay, all right. And then we had another one. When the user pulls a module written in another language, where is it compiled and executed? What are the security implications of running arbitrary code?
The security implications are it's better than you could possibly hope. Because WebAssembly itself does not have the ability to open up network connections. It doesn't have the ability to launch processes. It doesn't have the ability to read from the file system. So it only gets those abilities from the host environment that it runs in. That's why I say WebAssembly makes code portable, but WASI is what makes applications portable. Right? Just like Windows applications couldn't run on Linux until like the Wine project emulated Win32. But basically, as long as the environment that you run in has the WASI interfaces that you're looking for, then they can decide which directories do you get to read from. They get to decide whether you get to open network connections or not, or how you might open up network connections. So I honestly think that things like phishing attacks and certain kinds of malware are going to be very, 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 very hamstrung by these technologies. As far as the question of where do things get compiled, they get compiled into WebAssembly. And WebAssembly is notionally like bytecode, Java bytecode, or .NET CIL. It's in the host environment, in this case, the browser, where it's sort of the last mile handling. It will be compiled into whatever the native ISA for that platform is. So on this Mac, which is an Intel-based Mac, it'll be compiled into x86 instructions running within the context of the browser. So therefore, it can't read the file system or violate the same origin policy or anything like that as well. But the thing is, the WASI environments will be available whether you're running in a browser or not, whether you're running in Node or Dino or in an embedded system. And all you know is that something is providing you the functionality that you need. And for the purposes of, say, like reading a file system, that might be a file system abstraction over local storage or your S3 bucket in the cloud. Like, you have no idea where the stuff is actually stored, but you're able to ask for it using an interface, and that interface will provide implementation, and that implementation it's up to the host environment where and how it's going to allow you to do stuff like that. So hopefully that's enough of an explanation for now. But the security profile is actually going to be a lot stronger, and that's one of the reasons why I do think WebAssembly and WASI are going to eventually, not this year, not next year, but in the not too distant future, kind of eliminate the need for Docker. Because if you say I'm compiled against the expectation that my host environment is going to provide me these services, then why do I need to containerize that stuff? And I think the security profile of WebAssembly is much stronger than Docker is. So Solomon Hike even said if WebAssembly and WASI had existed, they never would have bothered creating Docker. So I still think market forces are such that there just won't be enough of a reason for it in the future. Not currently, but in the future. And we're already seeing Kubernetes like move towards having support for WebAssembly stuff sort of directly. All right, couple final things, and then I'll see if there are any more questions and talk about the Brave thing, since my thunder has now been stolen. Here is an example of IPFS Stack Exchange, right? And you could turn around and say, hey, I think this demo is not being maintained, so it doesn't work as well as it used to, which is kind of annoying. But you get the idea. Is like you can now publish stuff, serve it up out of there, have it be as dynamic as you want it to be, and as long as the content is available, it will be completely transparent. Now, if you're concerned about stuff going away, there are emerging markets called pinning services, where in essence you could pay, a nominal amount. It'll be certainly cheaper than hosting it on AWS and S3. You can pin the content, and in essence, somebody will keep it available. So it's just like a way of guaranteeing somebody has a copy of these blocks who's going to be there and listen for it. And that way you can build, distributed sanity checks around the availability of applications as well. So on the one hand, if you don't want to do that, you can just serve it up locally, and as long as you have a connection to your home machine, you can publish stuff there. If you want to pay someone to do it, then that'll be useful as well. And so what we're seeing is a whole set of communities and new market opportunities where, for example, from generation to generation, somebody may be the family genealogist or whatever, and they may point into things like ancestry.com or whatever, or they may just serve up their own stuff. But if that person passes away, it's entirely possible that somebody else will be able to take over the stewardship of hosting that up for somebody else. And so in terms of managing projects and content and sharing things, transferring digital assets intergenerationally is now being considered as something that people want to be able to support as well. Sorry, I think my trackpad is running out of juice here. All right. Give me a second, I'll get my mouse back. Any day now. There we go. All right. One final consideration, which is, if anybody's familiar with Fuse, Fuse is a user-land file system. So things like Dropbox and other tools like that use it, and it basically emulates a file system. It makes your computer think there's a directory with stuff in it, but really those things exist someplace else. And I'm sorry, off the top of my head, I have no idea if Fuse is available on Windows or not. I think it can be, but it's definitely available on Linux and Mac OS. So you can install it and, in essence, mount IPFS onto your local directory structure. And so now, notice I'm not using IPFS cat, I'm using regular cat. So if you think about this for a moment, you now have emerging ubiquitous computation in the form of cloud computing, edge-based computing environments like Fastly. You've got ubiquitous connectivity, right? WiMAX, 5G are emerging. You've got the ability to emulate file systems locally, even though the content is being served up from who knows where else. But we also have stability around that content being served up. And you can see how even for an organization, right? If you work for a reasonably large organization, chances are you have a SharePoint installation that people, it's like the Hotel California, right? You can check in anytime you want, but you can never get anything else out there. You lose track of links and people forget what's in there, and then you lose documents. Think about having an organizational history of documents that are available as you migrate from document management system to document management system. And maybe you just rely on the fact that internally you've got a bunch of extra hard drives lying around, so you can serve up the content from any of those hard drives. And you don't need to have a turnkey content management system like SharePoint anymore. That's an example of the kind of thing that's going to emerge. I'll leave these links here for you to go through, but these will walk you through things like, hey, let's create a web page and add it to IPFS, right? So you go through the whole process and you set it up, and then it's like, okay, cool. Now let's publish the name of the thing to IPNS, because I'm sure one of the next questions somebody's going to ask is, well, if you have the link to the old one, how do you learn about the link to the new one? That's where IPNS comes in. You've got the capacity to sort of link a name and then have it move forward to like the latest version as you want, but anybody who has the old ones can still point to the old one. So this link will walk you through, modifying web pages and republishing IPNS and things like that. So that's one way to manage change. The other is to use a technology called DNS link, where by using text records on DNS records, you can basically like leave placeholder connections between sort of more stable names, like the Lib P2p website itself is available through dnslink.ip libp2p.io. So in essence, that becomes the stable name, but you add text records to those DNS records to point to specific versions. So now they are all serving up their applications and web pages and stuff by tweaking which versions are being hooked into through these DNS text records. There's also ETH-DNS is a way of registering DNS entries through Ethereum blockchain system. So in essence, you could point to a transaction in the blockchain that indicates, I've now claimed ownership of this name, and this is the content that it links to. And so there's all kinds of bootstrap mechanisms for finding stuff like that. All right. So again, I'm assuming this is new to most of you. It may surprise you that there is a literal ton of people building stuff on top of it. And that's one of the reasons why I encourage you to pay attention, because we're talking about Web 3, right? Web 1 was static files on file systems. Web 2 was social media, sort of dynamic generated content, that kind of stuff. Web 3 is going to be decentralized, stable, and a heck of a lot more stable. And if you think about people who are, the unicorns of Web 2, I would argue that they are vulnerable to the unicorns of Web 3. And as an example of that, I'll talk about that in just a second. Many of you have probably seen me go to this web page before. This is a link to a ping of the datasets that are part of the linked data project. And in that, there is an SVG file, which again, text-based file allows you to search for what you're looking for. So I'm looking for DBpedia. I found it. It supports animation. So this shows how DBpedia links to all these other datasets. SVG is also a hypermedia system. So I can click on that and be taken to a description. This tells you like how to query it, how to download it. But notice they're also starting to link into IPFS. So you're actually able to store data sets in IPFS and be able to retrieve them as well. Then we have Filecoin Io. So this is to storage what the company that I built 20 years ago was to computation. So Filecoin is a decentralized storage network designed to store whatever you want. So think of it like S3, except geographically distributed at the block level, not at the like region level. A heck of a lot cheaper, but just as stable. And so basically they are now, and this is where the Protocol Labs people are planning to make their money, is by disrupting Web 2.0 unicorns like Amazon S3 or Dropbox or things like that. They're in essence renting disk space on fast computers with good network connections all over the world, and then going to the trouble of making sure that there's enough capacity so that, if you pay at a certain level, you can guarantee that your files and things like that will be available within certain kinds of service level agreements. So again, you don't have to have hosting if you can serve it up locally and pull it out through a local gateway. You don't have to have S3 if you can just store it in a safe, encrypted, geographically distributed kind of way. And also not be concerned about corruption or anything, because if somebody modifies the file, it's not going to hash to the same result. So there's a bunch of other things. People are talking about specific uses and where this might go. So this is really just a technology. In terms of ethical uses of the technology, in terms of business models, in terms of communities around these sorts of things, we're going to see a lot of variety, right? There's going to be a lot of positive uses. There's going to be negative uses. There are like allow lists and block lists and things like that get into it. But fundamentally, those aren't technical issues. Those are social issues. So it's really up to a community to decide what they're comfortable with, stuff being shared. But there's a ton of stuff happening. And if you go to awesome.ipfs.io, you'll see that people are doing things like file synchronization with Git-like interface in Fuse file systems, and blockchain marketplace for musicians, and local first end-to-end encrypted data diary applications, and just convert an article in the current tab to a readable form and upload it to writable nodes. People are just really innovating the heck out of this stuff. People are building games around this stuff. People are building virtual ecosystems, sort of like online virtual reality conferences, and sharing content through those. It's just really, really exciting. But people are also building databases and file systems and layered file systems and a bunch of stuff like that as well. So this company, Textile, has the Hub, which is a collection of a database built in IPFS that feels like MongoDB, dynamic directories that developers can create and persist on remote peers. So again, tying all these things together, we've got these technologies, they're combining into services. Those services are providing things that people are interested in. And there's just a heck of a lot more activity than you were probably anticipating. So finally, very quickly, I said that there was an anti-censorship aspect to this. In 2017, Catalan separatists wanted to have a referendum on basically breaking away from Spain, and the Spanish government said, no, we are not going to allow you to do that. And so people would like post it on a web page, and then they would seize the web page or the domain and shut it down. DNS is a centralized system that at nation state levels, they have the capacity to lock people down and not let you see stuff. So people started mirroring it. Then they were going after the mirror people and whack-a-moling them. Then it was published to IPFS. And I'm happy to say it's still here 4 years later. Erdogan wanted to shut down access to Turkish Wikipedia. So Turkish Wikipedia was published to IPFS, and somewhere down here there's a link like to a snapshot from a particular point in time. Here's what Wikipedia looked like back then. And so there's now an initiative to move all of Wikipedia to IPFS as sort of humanity's shared cultural history. Everyone in the world should have access to that content. And we do not want to let the governments of the world necessarily like shut people down to access to things that we all consider that are part of our shared humanity and history. So again, it gets pretty political pretty quickly if you want it to, but there's also a solid technological basis to what's going on here as well. So just a couple of quick resources. The Simple as Water site just has some links to stuff. Protocol School are a series of self-driven tutorials on the lower level protocols like multi-hash and Lib P2p and IPLD. And then there's a whole series of decentralized based technology websites and things that are available through that link as well. So my contact information is at the end of the slides, so feel free to get in touch with me. But I want to go back to this first slide. And I'm curious if anybody noticed, this is a tiny URL, and the tiny URL will expand to something else. But if you click on it, you should be taken to the ipfs.io gateway, which is pulling these slides off of the machine that I am currently presenting on. So if you've already grabbed the slides, you've already used IPFS and you didn't know it. So I'm not sure how much time we have for questions, but I am going to stop. Nope.
So yeah, we had a couple questions. Let's see, are there ways being developed to strike a balance between open and decentralized content, but doing something like publishing blacklists of content hashes of objectionable material?
There are lots of, how do I turn off screen sharing here? Just so this is driving me crazy. Or can you just take it back?
Let's see, I can close that.
There
yeah.
we go. Okay. All right.
And then maximize yours.
There we go. Sorry.
There you go.
So there are a variety of approaches to this. And it's a community-driven thing. So it's obviously a very diverse community. But there will be some aspects that give you that kind of control. But to some extent, you have to stop and think, do you really want that kind of control? Because if you have that kind of control to identify stuff, then other people do as well. And therefore they can take down things that they don't like just because they don't like them, right? Not because, again, this is why I think if you've ever read Daniel Suarez's Daemon and Freedom TM, he imagined a lot of this stuff 15 years ago. And the idea was their communities have social currency, like your reputation is a discrete digital value that you can exchange. And therefore, when somebody wants to apply upward pressure or downward pressure on stuff, they have to, in essence, kind of give something in order to do so. But the idea there is it's very easy to find people willing to in essence, support something like, free speech and documents and, whistleblower kinds of things, for which there's like a greater good. And you will not find as many people who are willing to exert some kind of social pressure to maintain stuff that people do find objectionable. So the idea is that, things that do add value and attract interest and attention, in essence, will be buoyed by that, kind of like upvotes on Reddit or something like that. And then things that people do not like, or, if it's something that's like truly objectionable, terrorism, child pornography, things like that, it shouldn't be hard to find people willing to exert a little bit of pressure to shut those things down. I will say though, it's early days in terms of that kind of control, but I think those sorts of systems will emerge.
Great. And then someone asked, what's the deal with Brave?
Oh, yes. There? Thank you. So, if you go to, I'll paste this into the chat. If you go into brave.com, just this past week, they announced that they've been working with the IPFS team to add support natively. So within Brave, the latest version, you can say things like, IPFS, QM, blah, 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 and it's able to resolve those things. And it's also, because it is a desktop application, able to, in essence, detect the IPFS node that's already running on my machine. And so it says, oh, I can use a gateway, but I see that you already have it running locally, so you want me to just use that. So in essence, it can delegate how it finds stuff to the local node, and then fall back to gateways if your local node doesn't have it, or for whatever reason can't get to it. So that's very exciting. Now, you don't have to use Brave. One of the reasons that they were very quick on moving from Go to JavaScript is that almost all the functionality, if not all of the functionality, is available in the JavaScript implementation as well. So obviously you can just run that in any browser, but it's nicer to have the default implementation in the Brave browser make that available. So I think the expectation is this year we'll start to see it show up into Firefox and Chrome and Safari, and well, I don't know about Safari, but maybe Safari. Certainly through extensions and plugins and things like that, it should be possible. But even if not, right, you can still use the JavaScript version of it as well.
Great. That's all the questions we have. So let's get on to the door prizes and go from there. All right. So you'll respond in the chat to confirm that you are here and that you can use the door prize. So the first one is the JetBrains license. You get a license for any of their products. And our first winner for this is John Fackrell. John Fackrell, are you here? Let's see, John, you got to respond in the chat. All right, let's just try Scott Greenman. Are you here? I got a long list of people to win. Scott Greenman, no, not responding. Okay, I'm going to keep going. Ngoba. Ngoba oh my gosh.
Scott Greenman is here.
He is. Okay. And Fackrell. Okay. So they're both there. Very good. A little bit of lag. So Ngoba then moves over to the Agile Learner. Are you here? Let's see. So Fackrell and Scott are there. Ngoba. INGOBA. I don't want to announce another winner because of the last prize. So I would hate to tear it away from someone's hand. Okay, so we're having a bunch of thanks coming in. If I can't get Ngoba over email, I'll select another alternate winner. I've got a couple here, but I don't want to say the names and disappoint people. So, okay, so that's it. Remember, next month we have James from Goldman talking about ultra low latency systems, and you'll see announcements on that shortly. Thank you all for coming and sticking through this great presentation, and thanks to Brian for presenting and all of our sponsors. So have a good evening, stay safe, and enjoy the new year.
All right. Thanks, everybody. Stay safe.